Hello everyone, my name is Böcker, and this is the next behind the scenes talk about our different projects. This time it is Cosmic. As usual, disclaimer, this is not about using the software. There are other talks. If you're interested in learning that, please refer to those. This talk is part of a series of talks. There have been talks about Sirius, Zodiac, CSI FingerID, Canopus, and now Cosmic. You might want to listen to the other talks if you want to know more details. For example, I have a much longer introduction in the talk about Sirius and Zodiac, and then we're using a lot of the results from the CSI FingerID talk, so it might be useful to listen to those first. For completeness, I'm showing this slide again. We know what this means. These are our design paradigms. One that is particularly important for Cosmic will be universality. I'll come back to that. Now, setting the stage, I showed this slide before. As I said, if you want to know more details, please see the Sirius talk. But for us to go over those things that we need very shortly, we are talking about small molecules of biological interest, which we will call biomolecules. We are analyzing them by liquid chromatography mass spectrometry. To find out about their structure, we are using tandem mass spectrometry. We are looking at high resolution data, or a better word would be high mass accuracy data. Everything better than 10 ppm is okay for us. The better the mass accuracy, the better our results get. We are talking about data-dependent acquisition, and this is what you get out of the box. We could also process other data, but not with a software that you can download. If you don't understand a word here, I'm very sorry. This is not a talk for people who are, let's say, trying to get an overview over the field. I might prepare such a talk at some time, but this is more for people who are already doing such experiments and want to know what Cosmic can do for them. One short explanation about the differences between Canopus and Cosmic. Both have totally different reasons to exist. Canopus is for predicting compound classes, and it's really, really good for that. In particular, it's giving you compound class annotations for every single compound, even for those which are not in any structure database today and won't be in a structure database in 10 years. That's cool. Cosmic, what we are talking about today, is for searching in structure databases again. So we want to have structure annotations with a single structure. And another reminder or note here at this point, Cosmic is in a way much simpler than Canopus. Canopus was pretty complicated with all this deep neural network stuff and so on. So I didn't talk much about the method details because I would have to explain to you why we use dropout instead of regularization and so on and so on. Loads and loads of machine learning details. For Cosmic, it's much simpler, and that is an explanation why this talk will be longer, because I can explain such details. I hope you find those interesting. So what are we talking about? We are back to searching in a biomolecular structure database. I assume we have a reasonable biomolecular database. We usually use one which is a combination of many publicly available biomolecule structure database. What we get as an input is both the database we search in and the queried tandem mass spectrum. Both of them are processed by CSI FingerID. We don't really have to care what CSI FingerID is doing here. We could use another in silico method as well. And then what CSI FingerID is doing for all the structures in here that pass some filter criterion, which could be either the monoisotopic mass or the molecular formula, which is determined by Sirius. In fact, it's determining several ones. That's a soft filter approach. But anyways, you get all the candidates back from the biomolecular structure database, and then you put a score on each of them. That's what CSI FingerID is doing. And then we are sorting those candidates by score. So the highest scoring, on this case lowest scoring, is ranked first, and that is what I will call in the following a hit. Yeah, it's a combination of the query MS spectrum plus an annotated structure, because from all the structures in the structure database, this is the one which best fits the spectrum. It might still be correct or incorrect. We don't know. It's not unlikely that the correct structure is not even part of our structure database, in which case we can't do anything. But let's simply forget about these other candidates for the moment. They were not the best ranked ones by CSI FingerID, and just ask the question, is this one, this assignment, this annotation correct or incorrect? Now, something that makes it a little bit easier to talk about that is if we think of it as a complete data set. We usually don't annotate a single MS/MM spectrum, but a complete data set. So we have loads and loads of spectra and tandem MS spectra, and we have hits, so best scoring annotations, and sometimes they are incorrect and sometimes they are correct. Obviously, we don't know that. And what our task is, by the way, that I'm talking about these data sets now doesn't mean that Cosmic only works for data sets. It also works for individual spectra, but it's easier to think about it. Okay, so what our task is, we want to assign confidence. So we have this hit, as I said, it's a combination of a spectrum plus an annotation, and we want to say if this annotation is probably incorrect or probably correct. And this is obviously not a 0-1 decision. So sometimes we are pretty sure it's correct, and sometimes we are mostly sure or a little bit sure or super sure. So there are differences. So what we will assign is some kind of score to that as well. And then what we can do with this score is we can sort those annotations according to the confidence score. Sometimes I'll switch back and forth between the hit and the annotation, because in the end of the day, we want to know whether or not this molecule is part of this data set. But in principle, this is a combination of the spectrum plus the structure annotation, because a different spectrum might have the same annotation and one might be wrong, the other one might be right. That's a detail. Let's forget about that. So how do we do that when we do spectral library searching? The basic setup is pretty much identical. I mean, we replace this large molecular structure database by a much smaller spectral library, and then our search engine is simply the cosine score, and we again rank all those candidates according to this cosine score. And then again, we only consider the best scoring hit, and I will call that library hit here, and then again, it might be correct or incorrect, because as I said, maybe the wrong candidate get a better score than the correct candidate, and sometimes it can also happen that the correct candidate, the correct structure is not even part of the library that we search in. So what we usually use there is we use some threshold. I know that people are using other tricks like the number of matching peaks and stuff like that, but let's keep it simple. Otherwise, it will just get more complicated, not really different. What people are using is a threshold such as 0.7 or 0.8, and then it might be a correct annotation. So what we are doing implicitly is we are again sorting by a score, the library hit score. The higher this library hit score, the higher our confidence. Because as I said, you might accept something with 0.7, other people might say, no, that's not good enough for me, 0.8. That means more confidence. So it's exactly the same as before, and you can formalize that, and you can actually compute false discovery rates from that. I'll come back to false discovery rate estimation much later in this talk, and I'll explain why it's super hard. I already indicated that several times. It's really a nasty problem, but here we have to deal with that in a little bit more detail. But nevertheless, it's better than nothing. We should always be aware that even if we find an almost perfect match in a spectral library or an annotation in a structure database, it might nevertheless be incorrect. Assume for a moment that this is our query spectrum, but this structure is not part of our structure database, or this spectrum is not part of our spectral library, or any spectrum corresponding to this structure. But our spectral library or our structure database contains data for this structure. What will happen? Well, we will put that in as a query, and we'll see that those spectra are an almost perfect hit. Okay, cosine score, if we leave out the precursor peak, is 0.99, above 0.99. So we would almost definitely say this is correct. And it is almost correct because all has happened here is that one single side group has moved by one carbon atom. But nevertheless, in our evaluations, this will be regarded as incorrect. I have to remind you that we do this evaluation in this way because we cannot really differentiate between a still acceptable thing and something that is completely wrong. It's not that easy. If you say, but I would learn something very useful from this data, then it's okay. Our method simply becomes better. Our evaluations would become better. Just keep in mind that we don't treat it like that. Now it's a rather obvious idea that we could do the same thing that we did for spectral library search, also for our in silico tools, such as CSI FingerID. I don't mind which one, any one. So we have the score of the highest ranked candidate. Can we use that to differentiate correct and incorrect hits? And this is more or less an outlook to what we will come back in a few minutes. We somehow have to evaluate now whether our methods can do that for you. Sorting by, say, the CSI FingerID score does, in fact, give us a possibility to differentiate between correct and incorrect hits. And I say this is an outlook because I first have to explain to you what I mean with these different bar plots. But what is shown here more or less is that it doesn't work. So sorting by those scores, and it doesn't matter which of the tools is used, will not allow you to differentiate between correct and incorrect hits. Actually, this is an artifact that this bar here for CSI FingerID is 30%. It doesn't really mean something. And I'll do another outlook, and that will be, I would say, the final results figures, which I will show you, because the other ones, the bar plots which I just showed, still have some issues. In here, what you can see is, and that's all you have to see for the moment, a method which more or less produces a straight line, doesn't matter where it goes to here, sorts hits rather in a random fashion, almost random, yeah, or worse than random sometimes. And all the different scores, all the different in silico methods do that, whereas a method that is successful and in sorting or differentiating between correct and incorrect hits will look like this, and Cosmic will actually look like this, even though we will ignore Cosmic for the second. So all the other methods are more or less random, and we should be aware that this is not a critique against these methods, their developers or whatever. I mean, we are ourselves developers of CSI FingerID, and the CSI FingerID score cannot differentiate correct and incorrect hits. That is simply, yeah, it happened because these scores were not developed for this task. This is not critique because nobody intended that they could actually do that. It would be nice if they could, but they can't, and so what? This happens. It's not really surprising. They were not made for this task. So yeah, just don't take this as a critique. Now, one more thing before we start. It is understood that candidates, there's a clear differentiation if you look at the score that the incorrect candidate gets and at the score that the correct candidate hits. And I have seen such plots already in publications, and these plots are hiding the fact that there are orders of magnitude more incorrect candidates than correct candidates. I mean, if you search in PubChem there and you have 10,000 candidates, then 9,999 must be incorrect, and at most one can be correct. So let's not normalize the two plots individually. Then you can actually see what is going wrong here. What happens if you can't even see the correct candidates anymore? So let's zoom in And this is now the zoom in. This is this area here, very much enlarged. And you see that the correct candidates are negligible in comparison to the incorrect candidates. And you always also find incorrect candidates which will receive extremely high scores. And that's because we are looking at candidates and not at hits. Okay? So all of that, to make it short, it doesn't help us at all. Obviously, a method that has a good search capacity that can actually find, annotate a reasonable number of correct structures will have such a plot, but that doesn't mean anything for differentiating between correct hits and incorrect hits. Okay? So before we start, we actually have to talk about false discovery rates. I already said that we have to make several of these detours so I can explain you why how well Cosmic is working and why the other scores cannot do that. Now here comes a very important point that I noticed many people don't get at the first glimpse. So I will spend a little bit more time on that. And that is when I will talk about false discovery rates throughout this talk. I'm almost always talking about exact false discovery rates. So many slides from now we'll come back to FDR estimation very shortly. But up to that point, we are only talking about exact FDR. And that means we are talking about the true numbers, not estimates. We have to play God to calculate those numbers. We have to know the correct answers to do that. We can only do that for reference data. But then how are you going to evaluate your methods if not on reference data? You don't tell the method what the correct answer is, and then you see how well the method behaves. That's what we do all the time when we evaluate CSI FingerID or Canopus. Okay? And this is true here too, so we can actually compute those exact FDRs. We don't have to estimate FDR. FDR estimation is only necessary in an application. You do no longer have to play God. You now don't know which of those annotations are correct and incorrect, and you try to approximate the exact FDR. And then you have to show that your method actually does a good job approximating that. But I don't know, in 15, 20, or 25 slides, we will very shortly talk about FDR estimation. But for the moment, simply forget that it exists. It's not there. Completely forget it. Okay? So how can we compute exact FDR? As I said, we have to know everything to do that. We assume that we had some queries. For each query, we found the best scoring candidate. It gets a score. It doesn't matter if this is now the CSI FingerID score or any other score. And then what we did was we sorted those hits by score. So this time assuming that a high score is the best. It doesn't really matter. And as I said, we have to play God. We know everything, so we know which of those annotations are correct and which of those are incorrect. So the red ones are incorrect hits and the green ones are correct hits. As I said, this is only for evaluation. Our method doesn't know about it, otherwise it wouldn't make sense to actually use it and try to search there. But if we now know this, we can decide for an arbitrary threshold and say, I think good score threshold is 10. Everything above score threshold 10 is assumed to be correct. Everything below score threshold 10 is assumed to be incorrect. Why would we do that if we already know which are correct or incorrect? Because our method doesn't know that. Our method simply assumes that by that it can somehow separate the correct ones and the incorrect ones. Okay? We know it, but not our method. So let's assume we have decided for a particular score threshold. The score threshold is not really important, but it's somewhere between here and here. Then we can calculate a false discovery rate. And what we do is we simply count how many hits are above the score threshold. In our case, for this threshold, it's 3 hits. And how many of them are incorrect. In our case, that's 1. And then the false discovery rate is simply the number of incorrect hits above the score threshold divided by the number of hits above the score threshold, which is 1 over 3, 0.3333. And for this score threshold, we would report 2 correct hits. We keep that in mind and look at a different score threshold. Now let's assume this is the correct score threshold. How many correct and incorrect hits do we have? Or how many hits do we have above the score threshold? That's 6. 2 of them are incorrect. So if we choose this score threshold, our FDR is 2 over 6, which is 1 over 3. Oh, that's again the same FDR. And that can happen many times, that the FDR gets smaller again if we lower our threshold for the score. For this score threshold, we would report 4 correct hits, by the way. So in application, we would assume that somebody has given us some FDR threshold, such as 33.4%. That's obviously a toy example, but I mean, otherwise we can't really show it with these few hits. And then we would search for a score threshold so that this FDR is held. We know the exact FDR. And as I said, since the FDR can get smaller again, we search for the minimum score threshold, the lowest score threshold, so that this is held, so that we are reporting as many hits as possible which are correct. So here are actually the FDRs for all the corresponding score thresholds, which are slightly below that. And since this is going up and down, which is not really nice, we usually then rather concentrate on the Q value, which is the smallest FDR, such that the corresponding hits, say this one, would be part of the output. And this one would be part of the output if we set the FDR as low as 20%. And that's also true for this one, obviously, because if we set the threshold here, then we have an FDR of 20%, and both are part of this output. Doesn't really matter for the incorrect hits, but just for completeness, I've reported them as well. So what now happens is we decide for this threshold and we report a particular number of correct hits. And this is now the thing that we would, that we could report if a method does something good or bad. How many correct hits does it report at a particular FDR? How many hits can this method report for FDR 5%? Or in this case, 33.4%. And we could report now it returned 4 hits, but then obviously this depends on the number of queries that we actually put in. How many queries did our data set have? 500, 2000, 4 might be good, 4 might be bad. So we would rather then report the ratio. And in our case, it's the ratio of the correct hits with all queries, because this is, after all, the number that you want to know. How many correct hits do you get back in your data set if you accept an FDR of 5%? And now we can explain this slide, the first result slide. It's now fully explainable. You should ignore Cosmic for the moment because we haven't talked about Cosmic. This will be what we will talk about later in this talk. But now you can see that the ratio of correct hits you get back by CSI, FingerID, CFMID, Magma Plus, and MedFrag is super, super small. And it gets a little bit larger here. As I said, this is an artifact, and I cannot explain to you why it's an artifact in this plot, because this plot doesn't show you the complete information. So as said, we can now plot these bar charts, and what do I mean with they hide information? This is now a toy example, another toy example, so I can nicely demonstrate what's not so good about these bar charts, why we have introduced something new. And the point is, we now have all this information about 5% FDR, 10% FDR, but what is about 11% FDR? Why is that important? I mean, why would I want to know that? Because results of a method can be really different for 9% FDR, 10% FDR, and 11% FDR. Or they might be extremely similar for these 3 values. We have no idea. So one method might look very bad in the evaluation and another one might look very good, but this is all just because how we chose these thresholds. And if we had chosen the threshold slightly different, we would have seen it's exactly the other way around. So how can we make sure that we don't miss that? that not our choice of thresholds actually governs what we see and what we believe. Now there are other plots that you can do here, and those are ROC plots and precision recall curve plots. And I have done that now for all of these methods. And as I said, this is a toy example. There are these 4 different methods. It doesn't matter which one is which. So there is nothing. I made those numbers up. Yeah. And I would say that the best method in here should be the green method. And then the blue also looks interesting. And yeah, the other ones don't look that interesting. So can you see this information in those 2 plots? Well, I cannot. I don't know how to see that. I don't know how to tell you that the green method is actually by far the best method if I look at this plot. And the problem with that is normalization. The normalization of those plots is not really the best one for the application or what we have in mind, which is compound annotation. And exactly for that purpose, we introduce hop plots. And I want to stress that we did not introduce hop plots to confuse everybody simply because we wanted to have a new plot type, but because the other plot types are not good for what we have in mind here. For the task that we have in mind, different methods annotate a different number of hits correctly, and then we have to assign whether a confidence score, whether it's correct or not. They simply do not work. But hop plots do, and they're actually quite simple. And we are back to the example that I showed when we did FDRR estimation, but here we will simply count how many of the hits above the threshold are correct and how many are incorrect. And then we will again normalize by the total number of hits, yeah, which is 8 in this example. So with this threshold, we have 2 positive examples, 2 correct hits above the threshold. 2 of 8 is 0.25 and 1 is incorrect, 0.125. Okay, just keep in mind we are normalizing by the total number of queries. And what we do now, since we cannot decide for the correct threshold, there is no such things, we do a plot that shows all the thresholds at the same time. And we start off with an arbitrarily high threshold, in which case we do not report anything back. And in this case, both the ratio of correct hits and the ratio of incorrect hits is 0. We then lower our threshold, and here we get 1 correct hit, which is now reported. And that is, we can simply step up in our plot by 1/8. Because our ratio of correct hits now increased to 1 in 8. Remember that we always normalize by all the queries in here. So if we lower the threshold further, then we'll get another correct hit, which means that we are moving up again. The ratio of correct hits increases. If we lower the threshold further, we get an incorrect hit and we move to the right here. And notice that we are moving to the right exactly the same space that we moved up before, 1/8. That's important. I'll come back to that in a second. We lower the threshold further, which means we move up because there's a correct hit added, another correct hit, so we move up, we move to the right, we move to the right, we move up. And then we hit, and that's always the case, this anti-diagonal here. So all of these curves end up in this anti-diagonal. And this is actually quite similar to a different plot. Oh, by the way, sorry, this part always stays empty. No curve can get in here, and so we usually use that for some zoom in for the most important area. And I'll come back to the most important area in a second. And the similar curve to a hop curve is the ROC curve, which I hope several of you already know. In a ROC curve, you always end up in this point, 1, 1, no matter how many correct hits are among all queries and how many incorrect hits are among all queries. But in principle, this is exactly the same curve, except that we squeezed it a little bit here. So we just squeezed this point to end up here by making the step size different depending on whether we go up or to the right. For going up, it's still, now it's 1/5, and for going to the right, it's now 1/3. So with 3 steps to the right, we end up in here, and with 5 steps going up, we end up there as well. Now the name hop plot stems from Humpulus lupulus, so the hop plants ranking up to these wires. We thought that it somehow looks like it. We also like the name because of the implication it has. And now I can demonstrate you that the hop plot contains all the information from the bar charts, which in general we like very much, but it contains also all the information that the bar charts don't show. For example, we have in here these lines, these dashed lines, and they are labeled 5% FDR, 10% FDR, 20% FDR, because that's exactly what they are. They are the FDR levels in the hop plot. And so if you want to know method 3, 5% FDR, where is that in the hop plot? It's actually here. It's also a blue triangle, and it's exactly the 11% that we reported here, because this is the last time that the blue line intersects this 5% FDR line. Okay, and so you can simply look where it intersects that, and that's exactly the number you report here. Or this one here. Method 2 at 10% FDR. Simply check where is the last time that the green line here intersects the 10% FDR dashed line. And that's actually here. And you see something quite funny here, because that is intersected at a point where actually 2 hits have exactly the same score. This will rarely happen in practice, so it's more a theoretical thing. Okay. But all of these other bars are also contained in here, but we also have those things contained in here which are not shown in any of those plots. For example, you can think of 15% FDR. Just put a ruler here, and then you will see where it actually intersects those lines. And why do I say the last time? Because we want to report always the largest set of annotations returned in case we have different choices. And here, for example, we have different choices. We see that the FDR is for a short moment below 20% FDR for the green method, and then it gets better again. And here's the last time that the green line crosses the 20% FDR. And we can see that there we would report 44% of all the hits, and we would report 44% correct hits among all hits. And by the way, we also see how good the method performs in total if we wouldn't use any ordering or any sorting of the confidence levels. And that's simply here. So there we don't use any score threshold, and then we would report 73% correct hits with this method. So this method is able to annotate 73% of the instances correctly, whereas these methods are much worse. But you can now differentiate if the performance is due to a method being very good in searching in a structured database or wherever, or because our confidence score or whatever we need to differentiate between correct and incorrect hit is doing a good job. So both rock and hop plots can be used in our evaluations. And whenever we compare different methods which have different annotation power, then we have to use hop plots, because otherwise we won't see if in total the separation by some confidence score or the score itself plus the annotation power of the method works better or worse for any given FDR. The same is true if we want to plot the performance for different data sets or different settings, such as different collision energies in one plot. Then we always use a hop plot because we end up in different points in the hop plot. But if we compare different versions of a confidence score, let's say the original CSI FingerID score against a confidence score or something like that, then we end up in exactly the same point of the hop plot. So that's boring. So we can instead use a rock plot, because then we use all the available space to show which of the methods has a better separation. So this is a reminder of the second result slide. And now we can really see what I promised you. I mean, what we see here is this more or less random performance of CSI FingerID. And now we understand why I said that the 30%, the good value for the 30% of CSI FingerID is an artifact. And this is actually an artifact of the fact that CSI FingerID on the complete dataset reaches almost 30% FDR simply because its search performance is so good. So this has nothing to do with being able to sort correct or to differentiate between correct hits and incorrect hits. It's almost doing a random job. It's just a random artifact. It has to cross this line if it's doing something random multiple times. And then we report the highest value there, and that's pretty good. But yeah, no, it doesn't work. The CSI FingerID score cannot separate correct and incorrect hits. And by the way, I already told you that the zoom in is pretty interested for us. And that is because usually we are interested in very, very small FDR values. And okay, the green line here, which you should ignore because it's cosmic, we didn't talk about that. But for that, we see that it crosses these different lines up here, and that's cool. But very often that's not possible. Very often the methods don't perform that well. And for that, the zoom in is interesting. So you actually see where different methods cross these dashed lines that correspond to different FDR levels. So we now enter the method part. So far, I just talked about evaluation measures and how we can actually show if a method does a good job or not. And now we start with trying to develop a method, trying to come up with a method that actually separates correct and incorrect hits. And the first thing you can think of, or if you know something about that, then something you notice that in proteomics, very successfully score calibration has been used. So people in proteomics have very similar issues. They also search in databases, they get hits, and they want to know whether these hits are correct or incorrect. And they also found that the score itself is not really a good measure to separate correct and incorrect hits. It has several shortcomings. And so different people had the idea of calibrating the scores. That means instead of simply saying the score is high or the score is low, you say how good would a random sample thing, whatever you're searching, in this case a random peptide, how good would a random peptide score against that? But okay, we have our score. So what can we say then? Something like a p-value. Okay, we simply see that certain query spectra produce different distribution of scores against randomly chosen peptides. That's simply because some spectra have more peaks or more noise peaks, more explainable peaks, more signal peaks, whatever. And that means they get better scores by our score metric. And so we should not directly compare those scores, but rather calibrate them. And calibrating them can be achieved by looking at the score distribution. As I said, we are looking at the score distribution of random peptides, and we have a certain candidate score which we have observed. And what we now check is the p-value, the probability that a random peptide would reach the score that we have observed or a better score just by chance. This is the area under the curve of the distribution that I'm showing here. And there are different ways how you can achieve that in proteomics for peptides. For example, there's a way of doing that exactly via dynamic programming. You have to do a few simplifications such as discrete scorings, discrete score values, but that's all solvable. It's then just an approximation, but that's good enough. You can determine it empirically by using decoys. You can actually model the score distributions. That's the oldest idea how to do that. And our problem here is that none of that really works for small molecules. But at least we can borrow some of those ideas. Now, I'm showing this slide because I might actually mention that in a talk, and I was once told that somebody got into a lot of trouble for mentioning this example. It's the monkeys with typewriters idea, and it's such a brilliant analogy that yeah, it's the best way of understanding what a p-value really means. And I show that to all of my students, and I hope that you find it useful as well. And the idea is you can randomly produce anything. You at least assume that you can randomly produce anything. This is not something special. I mean, somebody has to win the lottery. It's nothing special. And if we wait long enough and humankind exists long enough, then somebody will win the lottery 1 week after the other. Yeah, 2 weeks consecutive. And if we wait long enough, somebody will win the lottery 3 weeks straight, and so on and so on. What happens is it gets more and more unlikely. And one of the nicest ways of thinking about that is this monkeys with typewriters analogy, that if you have an infinite amount of monkeys with an infinite amount of time, or 1,000 monkeys, it really doesn't matter because they have infinite time, you will eventually write all the work that Shakespeare has ever written. It's just super unlikely that this will happen during any fixed amount of time. And so by looking at this amount of time that the monkeys needed to write something, you can judge whether it was good work or not. Obviously not, because I mean, this is just a joke in the end, but the idea should be clear. If it's pretty easy to end up with something as good as what you see by a random process, then it's not really surprising. So we have the issue that we can't really do decoys. There are now some possibilities to do something similar, autoencoders, and I could talk about that and why we don't like them. I don't like them at present. I'm not sure if they are really good decoys, but let's for the moment simply assume that we don't have anything like decoys. What are decoys? Decoys are things that are similar to the real thing, but produced by a random process. And for a random sequence, a peptide sequence, that's super simple. Everybody knows how to create a random string, a random peptide string. But how do we do that with a structure, a molecular structure of a small molecule? And we use a proxy for that. We use all of PubChem as a proxy of small molecules which are out there, but which are not the correct answer. And that's, yeah, somewhat dangerous because I mean it's possible that actually the PubChem structure is the correct structure and it is inside the sample that you used, and it's not inside your biomolecular structure database because so far nobody knew that this PubChem structure can be found in biomolecules. But as I said, it's a proxy, nothing more. We will see how well it works. And if we do that, we actually see that the score distributions of our CSI FingerID score look like a nice, well-known distribution, a parametric distribution. And in fact, it's a log normal distribution. Log normal looks a lot like a normal distribution, but on the right side, it has this hump. So it goes to 0 very slowly here. It's a heavy tail distribution. And this works for many of the distributions that you will look at if we get the candidates from PubChem. But sometimes it's not working. Sometimes these distributions are not as nice as a single log normal distribution. So how can we actually model those that have several humps? I mean, 2 humps is still okay, but there might be 40 humps or 10 humps or whatever. By the way, what I've shown here is the kernel density estimate. This is the blue line, which is actually a real log normal distribution with just the 2 parameters that a log normal distribution has. And that is already the answer. We simply use a mixture of log normal distributions, this kernel density estimate that I'm showing here as a nice plot, and compute the p-value using this kernel density estimate. And the cool mathematical trick is we never have to actually compute the kernel density estimate. We just want to know the p-value, and that can be computed without ever doing that plot, without ever computing that. That's why it's very fast. It's as fast as doing an average or something. So far, the good news. So that was a nice idea, and it turned out that it doesn't work. I mean, it works a little bit. It improves our separation. So as I said, these are now rock plots. They end up in 1, 1 here because we are comparing the same method, CSI FingerID, and we are just reordering the hits and nothing more. And yes, the calibrated score improves the ordering. I mean, this is a data set where the CSI FingerID score performs much worse than random, and the calibrated score performs much better, especially in this important area down here. I mean, who cares about those things that are definitely incorrect anyways? But it's not really much better because, as I said, we are interested in particular in this area down here. Yeah, that's where it should improve the separation, and it's not really able to do that. Why am I telling you? Nevertheless, why am I explaining to you how this works? We will come back to that in a few slides, but obviously it's not lost. Finally, we are there. I'm going to explain what Cosmic's confidence score is, how it works, why it works, and so on and so on. And I'm going to tell you a little bit about our struggles, because designing this confidence score, even though it's now super simple, took us something like 5 years. So the idea is basically the same as usual. We will use Voodoo Chicken. I mean, we won't use Voodoo Chicken, but you know what I mean. We will use machine learning in the end to decide whether a particular hit is correct or incorrect. And for that, we use the hit, or we have to describe it somehow. We have the query mass spectrum. We can derive information about that, like how many peaks are in there. We have the highest ranked candidate, and we know all the information about the other candidates, and we can derive some numerical representation whether or not a particular hit is correct or incorrect. And then the Voodoo Chicken has to decide, is it correct or not? And since we are pretty afraid of overfitting, we again restricted our Voodoo Chicken, our machine learning, to the simplest machine learning that is possible, which is a simple linear classifier. With that, overfitting is by far the hardest. Doesn't really matter which optimization you use there. I think they will all end up more or less in the same results. We used support vector machines, but logistic regression should give you more or less the same. And as I said, we describe now each hit by a few features, which you can find in the paper, like the score, the CSI FingerID score, score differences. We actually have 2 different scores now. We use both of them as features, but we also use the explained intensity. Are there many noise peaks, which we cannot explain in the spectrum? Then obviously the quality is lower, so it might be a bad spectrum. So we should reduce our confidence, or we might use fingerprint quality. We came up with a measure of if the fingerprint prediction is rather good or not so good, if it's unsure. And in 2016, 5 years ago, Marcus already presented this plot at the MetaBlanks 2016, and everything was looking so nice back then. Okay, back then we didn't have hop plots, so this is just a rock plot. But as I said, it's not really important here. We did that for independent data sets. We used structured disjoint evaluation. I talked about that in much length in the CSI FingerID talk, why this is important. So we thought we had done everything that you could possibly do to avoid overfitting. So we were super happy with that. And then during the next month, we applied it to several biological data sets. And that looked just horrible. It looked just completely wrong. And we had no idea why. Because, as I said, we had done everything that we could possibly do to avoid overfitting. So how is it possible that we get this much overfitting, crazy overfitting with a linear classifier with only 20 features, with a very low number of features, with thousands of training examples? We do it on independent data. We do the structured disjoint evaluation and so on and so on and so on. And quite honestly, we didn't have an idea back at that time. And more or less, this whole project went into hibernation. So I hope you enjoyed this short break. For us, it was a rather long and nasty break in which we really didn't have any idea what to do. And after several years, we came back to the problem. Actually, from this point on, Martin took over working on it. And we tried to find out what is happening there. Like, we had asked all our collaborators from machine learning if they could explain that, and they couldn't. And we asked, I don't know, statistics, whatever. Nobody could explain it to us. But at some stage, we found hints also from image processing that it's a good idea if you noisify your data. So in particular for us, this makes a lot of sense because we are just looking at reference tandem mass spectra. So those might be too good. I mean, those were measured from pure standards, and you don't have all the stuff that might happen if you measure a biological sample. So we perturbed that data. We came up with procedures to add noise. And with that, we at least faintly saw that something was wrong with our evaluation. But it was still completely unclear what was wrong. But a little bit later, we then got an idea what is going wrong. And that is only possible because we are using a linear classifier here. A linear classifier is just a linear combination of the input features. It just learns weights, and it doesn't matter which one you're using, they are all the same. And then if the value that comes out here is positive, then you have high confidence. If it's negative or small, you have low confidence. The exact values obviously depend, but that doesn't matter here. And here we can now really look at the weights that we assign to the different features because we are just training a linear classifier. By the way, I told you about this calibrated score, and actually the calibrated score is now a feature of our confidence score, but that's just a side thing. Anyways, we noticed something very strange, and that is worth looking at in more detail. And this is shown here. The fragmentation tree score is negative and the fingerprint quality score is negative. Now that's strange. Let's first concentrate on the fragmentation tree score. Sirius selects the best fragmentation tree score, the best fragmentation tree, the one that is returned to you, according to the score. The one with the highest score is actually the one that you get back. So a high fragmentation tree score is something good, obviously. But when we trained our confidence score, we do it exactly the other way around. The machine learning decided that when the confidence, that the fragmentation tree score gets smaller, actually our confidence increases, and the other way around. A high fragmentation tree score is suddenly something bad. How is it possible that these two things simultaneously hold? Obviously, it's not. Something went wrong. And there's more. For example, the confidence score is also depending on, as I said, the prediction quality of our fingerprint. So we made up a measure of the prediction quality where we again believed we made it so that a high value tells us our machine learning system has high confidence in the quality of the fingerprint, and a low value means it has lower confidence in the quality of the fingerprint. Yeah? So a high value of this measure should also indicate high confidence. That's the way we made it. But the machine learning model decided to use it in exactly the other way. So high confidence in the fingerprint means low confidence in the hit. How is that possible? Now, the point here is that we just came up with this measure ourselves, and we hoped that it would measure something like that, but it doesn't look like that. It's just measuring something completely different. Or another interpretation of this fact might be we don't have enough training data yet. Okay, the training data that we have so far is too little. So in total, we have no idea what is going wrong there, but we definitely know that something is going wrong. This is not the intended behavior. It should be exactly the other way around. So we don't know how to correct it, but we know for sure that we shouldn't touch this. And that is how now the confidence score optimization, the machine learning really works. And that is we decide for every feature beforehand whether or not we think that a high value of this feature should increase our confidence or decrease our confidence. So positive means high value increases our confidence, for example. The scores itself should increase our confidence, high values. And then there are other things like the calibrated score, which is then logarithm. So small values are actually better. So low value should increase our confidence. And we do that before, and we tell the machine learning optimizer that we don't want these features to be used in the other direction. So if it has to use it in the other direction, rather don't use it at all. And that will necessarily make our method look worse in evaluation. And that's what you see here. You see 2 times the same machine learning model trained, but one time it's unrestricted, so the one where we let the machine learning itself decide whether or not it should use a feature in this direction or that direction, and we have the restricted one where we tell the method in advance that this feature is good or bad. Okay, and you see now that it's worse. It performs worse. Like if we would look just at things such as the area under the curve of this rock curve, then the unrestricted method performs definitely better than the restricted one. But then these values are not always the best, and you have to be careful when reporting them, because what we are most interested in is actually this area down here. And in this area down here, those two curves are very, very similar to the point that it might be random stuff that makes one curve better than the other. And with that, this is the take-home message for everybody interested in machine learning. Our data makes it often necessary to take rather extreme measures against overfitting. That's not necessary in many other areas where you can apply machine learning. But here, and I could talk about that again for half an hour, there are reasons why we have rather extreme overfitting sometimes, and we have to take rather extreme measures against it. We should always be aware that optimizing the evaluation statistics such as area under curve is not an end in itself. It's showing you that some method is better or worse, but in the end, look at this part of say, such a curve that is really interesting to you and not just at some area under curve or something. Because in the end, those evaluation statistics may not really measure what we want, which is in our case, we want a lot of hits back at a very low FDR. And that's the lower left region of the curve. And we don't really care what the method is doing at 70% FDR. Nobody will ever look at that. Now we come to the evaluation of cosmic or the confidence score. And Before I start with that, I want to mention two things that you should always keep in mind. The first thing is all of the stuff that I will present you now is structure disjoint evaluation, which pretty much refers to all novel compounds, which means we never have seen a spectrum of the structure that we are currently searching for. You may want to listen to the CSI FingerID talk if you're not sure what I'm talking about here. And the second thing that is important here is that we never remove instances where the correct answer is not in the database that we search in. In practice, it can happen that you search for with a particular query, tandem MS, and the correct answer is simply not in the database that you search. And actually, that will happen a lot of times. We have no clue how good our coverage of biocompound structure databases currently is. So it will happen that the correct answer is not in there. And in this cases, the method should be able to tell you that it has very low confidence in the hit. Okay, CSI FingerID might come up with a solution because there's almost always at least some candidate in there, but the confidence core should be able to separate those and say, no, probably incorrect. Let's first compare Cosmic's confidence score to the CSID FingerID score and the calibrated score. And we see that it's performing much better. It's also performing better in the region we are most interested in, which is down here. This is now for different data sets, different collision energies, and so on and so on. This is for independent and cross-validation data, again, for different collision energies. And you can look at all of those details through the paper. I'm not going into the details of what exact numbers are shown there. What is really important is that these curves that I show you always look like this. It really depends like how easy or hard it was, how good the data was, how bad the data was to search there. But in all of the cases, the curves look more or less like that. The best looking one is CASMI, but it's also the very small data set. But we see that indeed our method of separating correct and incorrect hits is doing something useful, very useful. So it's returning a large number of hits at very low FDR. And why am I not talking too much about the actual numbers? Because these numbers are super dataset dependent. It depends on the query spectra that are in this dataset that you use for evaluation. It depends on the structure databases. Are there many candidates? Are there few candidates? It depends on how many of those can you actually annotate, because we are never throwing away anything, even if the correct answer is not in the database, because that is something that might happen. I mean, you have a query, the correct answer is not in there. Bad luck. Then the method should find out that, ooh, I don't believe in this annotation. I rather sort it to the low confidence stuff. Okay, that's very important. So we shouldn't think about these numbers too much. But what is important, as I said, is that even for such a data set, this is a particular data set, SciEx data set, where the performance of CSI FingerID is really bad, and the performance of the calibrated score is random. Yeah, even there, this confidence score is doing a pretty good job in separating correct and incorrect annotations. And here you might say, but why would I use the CSI FingerID score if it's worse than random? Because we don't know in practice if our data set looks like the size data set. I mean, this is because we are currently playing God. We are doing an evaluation of the quality of what our method is giving you. In practice, you wouldn't even notice. You would get totally crappy results. All the wrong results would come out first, and you wouldn't notice it. You would never know it. And one of the reasons why the performance or the separation is not that good for this data set, even for the confidence score, is that the annotation rates of CSI FingerID for this data set is fantastic. And if the annotation rate is that good, it gets obviously also harder to separate correct and incorrect annotations. It's not that easy anymore. All of them look pretty good, even the incorrect ones. Something else that we found was that somehow spectral quality has an influence on our separation between correct and incorrect hits. But this separation difference is much smaller than the difference in annotation power of CSI FingerID. So we looked at how many fragments, how many peaks do we actually see in the query spectrum above a reasonable threshold. And if there are few peaks, the annotation rate goes down for CSI FingerID considerably. As I told you, the annotation rate of CSI FingerID can be found on here. And the further to get to this point, there would be 0% correct annotations, there would be 100% annotations. So we are going down a little bit here with the annotation rate. It gets better for the better spectra, but the separation itself is quite good even for the spectra that have very few peaks. So that's a somewhat surprising fact. Now, something else that we found quite nice, or that gives us a good feeling of giving this method out to you for using, is that we looked at those cases where we made errors, where we said with high confidence this is a correct annotation, but then it turned out to be an incorrect annotation. What do I mean with unforgivable mistakes? Now let's assume we want to annotate animals from pictures, and let's assume this is our query's picture. Then we would not be totally happy if our method outputs this is a finch, because it's not, but it's a sparrow. But at least, I mean, it's not that crazy an annotation. It's still a bird. It's a somewhat similar looking bird. And so it's not nice, but it's also not totally crazy. On the other hand, if this was a query picture and our method would give us the output, this is a giraffe, I think we would think of the method of being a little bit crazy, right? How could it possibly, get this wrong? But it gets even worse. What about a method which now tells us that those two annotations are both with high confidence, where it tells you, I'm 100% sure that this is a giraffe, or 99% sure. Nothing is ever 100% sure. That would be nasty. So we looked if our high confidence incorrect annotations are rather forgivable mistakes or unforgivable mistakes. And this is now the highest scoring incorrect annotations, or the ones with the highest confidence score. And you can look at that in the paper. I'm not going into the details, but actually those are annotations where the correct structure and the structure that our method annotated are super similar. Like very often you can simply remove one bond and then put it somewhere else, and then you end up with the other structure. And that means I would say those are all forgivable, or these are pretty the best forgivable mistakes that you can possibly make. By the way, I mean there are loads and loads of correct annotations in between those 9 incorrect annotations, hundreds of correct annotations. And what you also see is in many cases, those are the ones that have a star here, the correct answer was not in the structure database. So the method CSI FingerID didn't have a chance to annotate the correct structure. Bad luck. So it did its best and found this one. And then the confidence score said, well, I see this annotation. It's probably correct. It looks very nice. And there's nothing speaking against it. There is not the correct thing that could say, no, there's something very similar. You shouldn't be too sure. Now, we also evaluated against library search. The difference so far was that all of the evaluations were carried out structure disjoint, which means, as in the case of CSI FingerID, we searched always assuming that the compound or the structure is not contained in our training data. Structure disjoint. I mean, obviously the spectrum itself is never in our training data. Watch the CSI FingerID talk for these differences, but we went several steps further. We assumed that the compound with a different spectrum is not in our training data because the spectra will be super similar. That would be too easy. That would be like library search. And in fact, the structure, the 2D structure, is not even in our training data. We almost ensured that. So all of what you have seen so far is for novel compounds. But you can obviously also use CSI FingerID and Cosmic for the same purpose that you use spectral library search, dereplication, stuff where somebody has already measured the same compound and it's in some public library. And I really mean public spectral library here. I don't refer to in-house spectral libraries, and I believe that those in-house libraries where you have measured both the tandem mass spectrum and the retention time of the compounds, I mean, they will be very helpful for many, many years, and I hope that we will have support for searching those shortly in serials, which would be very helpful, I think. But what I'm talking about here are large public spectral libraries, also commercial libraries, where the compound has not been measured on your instrument, and also you don't have recorded the retention time for exactly your instrument. And this are the results of this search. You now see here the two variations of the spectral library search. I mean, many people don't use the intensities of peaks themselves, but rather the square roots. That has a lot of advantages. So we evaluated both of that. You see FingerID here, and then you see Cosmic here. And again, this is now a data set, different data set, independent data set. So there's no overlap in spectra whatsoever between the training data of Cosmic CSI FingerID and the data that we use for evaluation. And similarly, obviously, we don't search for a spectrum in a library that contains exactly this spectrum, because then we would get 100% correct identifications, because they would have 1.0 dot product. Anyways, what we see here is indeed that Cosmic is giving you a much better separation. You get a reasonable number of compounds there returned at 5% FDR, like almost 50% of the compounds. That's really, really good. Yeah. And you have to keep in mind that the number of correct hits that FDR search can reach here is smaller. It's shown here because it can only find those things that are in the spectral library, whereas CSI FingerID and Cosmic can find more, like 10 percentage points more. This is this star here, because they search in a biomolecular structure database. Now I've come to notice that people think this comparison is unfair. I have the feeling that this goes to the point that you are not allowed to say that your method is performing better than library search. I don't want to be a heretic. So if you don't like what I'm telling you, it's totally okay with me if you completely ignore that. But what I can tell you about is that this comparison is as fair as it could be made possibly. Some people told me that they are using the dot product slightly different. For example, there's this minimum number of matching peaks things. Or you could actually search only for those compounds in the spectral library where the fragmentation energy, the collision energy, is the same as the collision energy of the queries that you did. We did a lot of these modifications. It never really improved library search performance to a point where we would say, hooray, this is now something completely different. So the general picture will simply be the same, I'm pretty sure, no matter what modifications we do. The second argument is even funnier, and that is Cosmic can find more things because it searches in a much bigger database. So I showed you that the total number of things that Cosmic can find is larger. But this is actually exactly the other way around. The larger the database you search in, the harder it gets to search there. We tried doing the same thing that we did for the biomolecule structure database for all of PubChem. You can look at those evaluations. They are really bad in comparison. I mean, obviously now the total number of compounds that you could assign goes up to 100%, but there are so many more candidates. It gets so much harder to find the correct one that CSI performance simply gets much worse, and Cosmic cannot really do something. It also gets harder for Cosmic to see which ones are correct and incorrect. So if spectral libraries gets larger, actually I think that the separation through the score, through the library hit score, will get worse for library search as well. And then there's the last and ultimate thing, and that is you must only evaluate for those compounds where you find a reference spectrum in the spectral library. And I can only say, what? That doesn't make sense. I mean, through all the evaluations that I showed you so far, we never removed those instances where the correct answer is not in the database that we search. This is just what you get. This happens. Bad luck. Live with it. I mean, if you search in a biological data set, you can't first remove all those where you don't have any hits. You don't know which of them are not in your spectral library. You search all of them and you hope you find hits, good hits. But it might happen for many of those queries that they're not in your spectral library. So this is what you get. Okay, after this comparison against spectral library search, let's think of you want to use Cosmic, the confidence score. How do you actually do that? A few words on that. One thing that many people asked is, or the reviewers of the paper also asked, which is the correct confidence score? Like, what confidence score is right for me? Well, I already told you this is not a one-size-fits-all situation. We can just give you some rule of thumb. Confidence scores above 0.6 definitely mean it's a high quality annotation. It has something we don't know, FDR maybe 10%, maybe it's 20%, maybe it's 5%. You can never be sure. That depends on your data set, but at least it's reasonable, good annotation, and you should rather think that it's correct than it has a 50-50% chance. 0.35 already means okay confidence. It then means that 20% FDR, at least this is now taken from one data set, this plot, so this is not the true for your data set. But nevertheless, you can expect that still the large fraction of those annotations are correct. Yeah? But this is really just the rule of thumb and not more. And you should use other means to check whether annotations are correct. And we use two other means to check that. And one will become available shortly with this Epimetheus, and the other one is already there, that is Canopus. Because, I mean, the confidence score cannot do magic. And you will observe one particular thing. When there are many candidates, the chances that Cosmic has very high confidence in a hit will decrease. This is by design, and this is absolutely what you want. This will not change in the future, because the higher the number of the candidates, the more you tell Cosmic that if there is a slightly almost identical structure, then you cannot be really sure that this is your correct structure. Remember, only the structure where everything is at the position where it should be is regarded as correct. We might add at some time another confidence score which tells you that an annotation is almost correct within this and this distance, but this will be in the future. On the other hand, you might notice that sometimes Cosmic appears to be overly confident when there are few candidates only. And this is something that we noticed and that we will fix in the future. It might already be fixed in the release you are using. But then there are other means, and as I said, Epimetheus will be available shortly to filter out wrong annotations, incorrect annotations. So if you notice that the structure that CSI FingerID assigned and that Cosmic told you has very high confidence doesn't agree with the compound classes that Canopus assigns, then trust Canopus. Don't trust Cosmic. Yeah? In doubt, Canopus is correct, because Canopus, during its training, it's very complex training, it's very complex setup and so on, it has seen the world of all the structures, more or less. I mean, at least very many million structures that it bases its decision on. Whereas Cosmic, it is at that point only seeing the structures which you presented as candidates from the molecular structure database. So there's good reasons why Cosmic sometimes goes wrong. But in the end, Cosmic, CSI FingerID are means to help you, and you have to understand that obviously all those annotations are putative. And in the end, you have to decide whether it's worth to do extra experiment. You can use all your experience there. You can make additional experiments. You can say, no, this is not going to happen in this organism. This is all stuff that we don't use for a good reason. And I'll definitely make a separate talk about that at some stage. But sometimes you might be able to sidestep all of this. If you find out that a particular compound is the one that might be responsible for some bioactivity, and you can commercially buy that compound, why do you really want to make sure that this is the compound that was annotated? I mean, you can simply test its bioactivity, right? And then you have completely sidestepped the structural elucidation and simply found that this compound is responsible for this bioactivity. And that was the question that you originally wanted to solve, and not, is this peak really this annotation? Final chapter, Cosmic is more than just a confidence score. In the paper, there's a figure for the Cosmic workflow. And there's one particular panel that we have not considered so far, which is up here. If we zoom in, we see we have to choose the structure database to search in. This can either be structure database of known structures, such as the biomolecular structure database that I'm talking about all the time, or it can be novel structures. There are different ways of how you can generate them. Currently, I think this is the most interesting, and that's actually what we showed in this paper, what you could do with it. And what is that? So the last part of our journey starts off with a publication from 2020, where the group of Peter Dorestein found that there are actually 4 novel bile acid conjugates that nobody knew about before that point. That was very interesting because people had done decades of research in this direction, but nevertheless missed them. And this inspired Louis from the group of Peter to generate hypothetical bile acid conjugate structures. He took different bile acid scaffolds. He considered different modifications of those scaffolds, say by phase 2 metabolism. He considered a large list of conjugations. And then he put all of that into a computer program, Smilib. You could also do it with other means, but it doesn't really matter. Describe to the program what he wanted to generate, and hit the run button, and off took the program and produced a rather long list of bile acid conjugate structures. And if you do that, you end up with 28,630 bile acid conjugate structures. This is less than an hour of computation, I would say. If you implement that very well, you might even get it down to minutes or something, or seconds, but it doesn't really matter because the other steps are much more time consuming. Do you see all the 28,000 structures here? Probably not. So let's zoom in a little bit. Okay, this is 2-fold zoom in. Okay, 4-fold zoom in, 8-fold zoom in, 16-fold zoom in, and now at 32-fold zoom in, you actually see something, but unfortunately, this is now only 0.1% of all the bile acid conjugate structures which we generated. As I said, generating those structures was not a hard part. So generating those 28,000 bile acid conjugate structures was relatively easy, but those are hypothetical structures. We don't know if they are real or not, if they are in any biological sample on Earth, if any organism on Earth ever produces them. So that doesn't really help us. Yeah, which of them are real? If only we had a method which could tell us that these bile acid conjugates are indeed in some biological sample. And as it happens to be, we already have such a method, and that is called CSI FingerID. Because with CSI FingerID, we can now take an arbitrary data set. We reused a mice fecal data set, which is publicly available in GNPS from Tipatia et al. From 2018. We applied CSI FingerID and searched this time in the bug structure database as our structure database instead of the biomolecular structures. And with that, we indeed came up with 626 bile acid conjugates which were annotated. But obviously not all of them are real. CSI FingerID will return the best scoring candidate, even if the best scoring candidate is completely off, totally wrong, obviously wrong. But if it's the best scoring candidate, this will be the hit that you get by CSI FingerID. So if only we had a method which could differentiate between the correct and the incorrect hits. Oh, we have such a method because it's called the confidence score. It's part of Cosmic. So we sorted them by confidence score, all the hits, and then considered the top 12. You have to remember that everything up to this point is done totally automated, or let's say fully automated. I mean, somebody has to start the analysis, and it all runs in a matter of hours. That doesn't take long, the whole computational analysis. The potentially the most tedious part is now checking whether or not Cosmic did a good job. So are those annotations, those top 12 annotations, correct or incorrect? But the nice thing is you don't have to do that for all the 626 annotations. Most of them will be wrong, and you will be really depressed after looking through 100 and all 100 are incorrect. Now you can really look at those, consider only those that are most likely correct. And so that's why we concentrated on the top 12. And again, Lewis had to do the tedious part and check whether our annotations are correct. What made it a little bit easier is that bile acids conjugate fragmentation is relatively well understood, so it's not that complicated. Also, we give you the correct structure, or the putatively correct structure, with this mass spectrum, and all you now have to check is whether or not our annotation through CSI FingerID is correct or not. And according to Louis, his manual analysis, 11 of the top 12 annotations are correct. So we annotated 11 novel bile acid conjugates. We are not totally sure. I mean, there might be some isomeric changes that do not influence fragmentation. So no tandem MS-based method can be sure whether it's this structure or a slightly different one. But up to this point, Louis was sure that these are the correct ones. I think it took him about a day to check all of that manually. And luckily, we had synthetic standards available for two of them. And that is due to Emily Gentry, who synthesized those and then made sure those synthesized are indeed the structures that we are looking at. So we could confirm those annotations by those synthetic standards, which still does not mean that we are 100% sure it's this structure, but again, as sure as retention time and tandem mass spectrum can get you. Now, this is pretty cool, and I'm super thankful to Louis to come up with this great idea of looking at bile acid conjugates. But I always thought there should be more like that. Isn't there other structures that people are interested in, that people have always believed there should be some structures that look like that I can easily describe, as I can describe bile acids by putting together 1, 2, 3 things or something, modifying a little bit, and then I can combinatorially generate all the structures. It would be really nice to get to know more of these examples, if there are more of them. Like if you say, I always wanted to know if this family of compounds or this compound class with an OH group exists anywhere in any biological sample, that's something we can easily try. And as I said, it won't take us very long. So if you have such examples, please tell us about it. Okay, now we come to the very last point, FDR estimation. I told you so far everything I have talked about when I talked about FDR were exact FDRs, nothing estimated. And when I talk about FDR estimation here, I can only tell you it doesn't work. And I'm convinced that this has nothing to do with our inability to do FDR estimation. I'm convinced that this is because it will be impossible for small molecule mass spectrometry annotations. But like, if you're not interested, this is more or less a negative result. You can completely forget about it. If not, be my guest to hear why I think it's impossible and what we actually did. Okay, so what does estimating statistical significance, estimating FDR actually means? It means that we try to approximate the exact FDR without being omniscient, without having all the information, without knowing which hits are correct and incorrect, which obviously in any biological experiment we don't know. So you could approximate FDR, you could also try to approximate other statistical measures like p-values, posterior error probabilities, etc. pp. Actually, false discovery rates were very successful in proteomics and genomics because they can be nicely been estimated without being omniscient. And there's all this target decoy approaches in proteomics. There's empirical base, there's Benjamini-Hochberg corrections for p-values in genomics, and so on and so on. Now, one thing you have to consider is that an FDR estimation method is an arbitrary method that returns values between 0 and 1. So, for example, if you give me a hit and or a list of hits, and I throw some dice and make a random number and give you back a random number between 0 and 1, then this is a valid approach for FDR estimation. It's a bad one, it's a useless one, but it is FDR estimation. And it's really nasty that a lot of papers claim to do some significance estimation without ever evaluating whether the estimated significances make any sense. And to do that, you again have to evaluate the method using data where you know everything, reference data. And then you have to show that your FDR estimate is accurate. And you have to show how accurate your FDR estimate is. As I said, half of the papers do that and it doesn't look good, or less than half of the papers. The other half simply claim that they have some significance. And it looks like many readers are happier if you don't show them how bad something works. But this is important information in my eyes. Now this plot is just to show you how such a plot then in the end should look like if everything goes according to plan. That's from proteomics, so it has no connection to what we are doing, but you see that the estimates and the true line here, this is true Q value versus estimated Q value. I told you Q value is better than FDR. Let's not go into the details, but true and estimated Q value are very, very close to each other, particularly in this highly important range between 0 and 0.1. And these are exactly the same plots, but now for our method. It's relatively straightforward how to transform the confidence score into such an FDR estimate. And what you see here is the curves are relatively close to what they should be for the cross-validation data. But if we go to the independent data set and try it there, they really, really look horrible. By the way, the horrible part is here more the end, that it's so far off. It's not this part. This part is more or less an artifact again, because our data set is still not big enough. So we don't have so many annotations with very low true Q value. Now, this is not much different from what you get when you do spectral library search. As I said, we have a paper where we describe how to do significance estimation for spectral library search. And again, there you see that it's particularly bad in the lower range here, very low true Q values, estimated Q values. There it doesn't work. So for low FDR, our method also didn't work particularly well, but at least you know how well it is working and you know what to expect and what problems you have to expect. Yeah, that's the nasty range. And I would argue this is not a problem of our methods, neither of the method for Spectrum FDR assignment, nor of what I presented you now for Cosmic, but it's a bigger underlying problem which nobody can get around. FDR is a statistical measure. And to apply statistics, you have to assume that something is happening at random. And our assumption is that incorrect hits are random. And otherwise, it doesn't really make sense to talk about FDR and FDR estimation. So you may remember this example that I showed earlier in this talk. And what this example shows is that our incorrect hits will usually not be random. Much more likely explanation is that you don't have the correct structure in the database you search in, but you have something that is very, very structurally similar and hence fragments indistinguishable. And that will be probably the predominant driver of incorrect annotations. I assume that, but I'm 99% sure, so you can never be 100% sure. And so I claim that accurate FDR estimation for small molecule MS simply cannot work. But wait, I've told you so much about all these other FDRs all through this talk. What about those? Well, those were exact FDR values. Those are correct by definition. I just used the definition of an FDR. So they are perfect. They are totally perfect. It's just FDR estimation will probably not work. One last word, because I always wanted to make a talk about that and I never really did. I should do that at some stage. I want to tell you that CSI FingerID throughout all the evaluations that we did is not using metascores. Metascores are scores that are using things like citation frequencies, or production volume. They have nothing to do with metadata, by the way. Metascores, except for the meta, there's nothing about metadata in them. Okay, so metascores, in my eyes, are a very, very dangerous thing. To this end, we don't use them. CSI FingerID does not use them. Cosmic does not use them. I mean, it doesn't make sense for Cosmic anyways. I showed you this example of the bile acid conjugates, and they researched in a structure database, and all the structures were novel. There is no production volume for a hypothetical structure. And if there's a production volume, it doesn't mean that it's present in the biological sample. Yeah. So in short, the argument is that these metascores tend to annotate only the blockbuster metabolites, so you see the same stuff over and over again. And actually what you could do, if you believe in these blockbuster metabolites, you can as well leave out the tedious MS, just measure an MS. Okay? If you think that MS1 is enough to annotate novel structures, then use metascores. If you don't believe that, I would be really, really scared to use them. And with that, we come to the end of this much too long talk. I'm very sorry about that. So I presented Cosmic. In the end, it's a very simple linear classifier, which took us 5 years to develop. It was really, really hard to come up with something that simple. And it was really a lot of work to keep it this simple, but that is why I believe that it will be very useful in practice, to differentiate to separate correct and incorrect annotations. And I hope you will find it helpful. I thank particularly again the Deutsche Forschungsgemeinschaft, which unfortunately cut down the project to half, but at least they are still giving us some money for it. Wasn't so successful, I assume, with only 2 Nature Biotech publications. Anyways, I particularly thank Martin, who did pretty much all of the work that in the end resulted in what we call Cosmic. Markus initially started off with a confidence score like 6 years ago, and then we had this depressing long break where we didn't know what to do anymore. And Louis came up with this wonderful example of bile acid conjugates that really demonstrated nicely the power of Cosmic and the confidence score. With that, it's over. This is the end. And currently, I don't know what method I'm going to present next. I have no idea. Maybe it's Epimeters, which will be a combinatorial fragmenter that we will release shortly. Maybe it's El Gordo, which the name is not even totally finished. I don't know. It's the fat one, so you might guess what El Gordo is about, but it's not really a new method from our side. So maybe not the best thing for a behind the scenes talk. But anyways, I thank you very much for your attention, and I hope you enjoyed this too long talk.